Good afternoon. This is Math 2413. A couple of announcements for today's lecture at the beginning, and then we'll get on with our lecture. I want to remind you that homework 5 is due, and I've kind of postponed the date on that, and so it is due on November the 21st. That's next Tuesday. That's the last day of the week, next week, before our long Thanksgiving weekend. So please kind of keep that in mind. I do have Homework 5's assignment that's due written here again for you in case you've missed it somewhere. But you've got those 9 problems to turn in. I do want to point out that section 4.10, those are on max-min problems or optimization problems, and those are all word problems, so you really need to get started on those. And if you have any questions, don't hesitate to come by my online office. I'll be happy to help you out. Or shoot me an email, and I'll be happy to respond to your email, see if I can help you out with some of these problems. The Exam 3 review will be posted by the end of the week, this week. So be looking for that, probably Thursday or Friday of this week. And then let me remind you that the Exam 3 testing window opens the week after Thanksgiving. So it'll open November the 30th and run through December the 5th. So we're rapidly coming up on the end of the semester. Just a couple of more lectures left for the semester. Today, what we're going to do is we are going to, first of all, go through a quick review of some of the things we talked about last time with the definite integral. And then we are going to move on and look at the connection between definite integrals and area. Finally, move into the fundamental theorem of calculus, parts 1 and 2, and talk about what those mean and their implications for us, especially for evaluating definite integrals. And then finally, we'll finish with a couple of brief applications for the definite integral. So let's go ahead and get started, and let's jump into this. First thing is the definite integral. Remember that a couple things we talked about from last time is that if you have a function, or if you have a definite integral like this, the integral from 0 to 1 of x squared plus 2 dx, that what we talked about last time was a general format. This is kind of a simplification, but we approached the definite integral using subintervals that were the same length. So equal subintervals or equal widths for subintervals. And we also use right-hand endpoints for heights of rectangles. Now remember, we do not have to make those simplifying assumptions. We did that just to write out the form in a little bit simpler version of the form for the definite integral. But we made those simplifying assumptions here. Didn't have to do that. The widths of the subintervals don't have to be the same, and we don't have to use right-hand endpoints for the heights of the rectangles. Don't have to do either one of those things. We chose to do that just to make our form a little bit simpler. Even though we've done that, it's still not a simple form, but you have the limit as n goes to infinity of the sum as I goes from 1 to n of f of a plus I times delta x, like this. Remember that this is the general form for an integral that looks like this, the integral from a to b of f of x dx. Remember that delta x, the width of each subinterval, is defined to be b minus a divided by n. All right, so in our particular problem, to go through and actually evaluate the limit of this Riemann sum, remember that sum is referred to as a Riemann sum. What we would do here is write out a little bit more specific of a version. First of all, we would calculate delta x in our problem to be 1 minus 0 divided by n, or 1 over n. And so this would be the limit as n goes to infinity of the sum as I goes from 1 to n of f of a is 0 in our problem, so it'd be 0 plus I times delta x, and delta x is 1 over n, and then delta x is 1 over n right there also. So you have that function value times the height of the rectangle. Remember that this function value, or times the width of the rectangle, I'm sorry. So this function value represents the heights of the rectangles, if you're thinking about this in terms of area, and delta x is the widths of the rectangles. All right, so this ends up not being too bad. We looked at some pretty messy ones last time, but this is the sum as I goes from 1 to n of f of I times 1 over n times 1 over n. Our function's not too bad. It's x squared plus 2, so this is the limit as n goes to infinity of the sum as I goes from 1 to n of I times 1 over n, quantity squared plus 2, put brackets around that, times delta x, which is 1 over n. So let's see, we go through and do the arithmetic here. We're going to try to evaluate, first of all, this sum, and then take the limit. So you've got I squared over n squared plus 2 times 1 over n. And so that gives you the limit as n goes to infinity of the sum as I goes from 1 to n. Multiply that out, you get I squared over n cubed plus 2 over n. Or I'll probably write that as 2. Yeah, 2 over n would be fine, just like that. Now remember, the idea is to use some formulas that you have to evaluate this sum. So let's see, we have the limit as n goes to infinity, sum as I goes from 1 to n. Remember, you're trying to write those out, and let me erase that here real quick. We're going to write this as 2 summations, and we're going to take these constants out. So you have 1 over n cubed times the sum as I goes from 1 to n of I squared. Remember, I is the variable for these sums, and so you can't take that outside of the sum. And there's no variable in the second term, so this is just 2 over n times the sum as I goes from 1 to n of 1, like so. Now don't forget, you have summation formulas that you can use, and these are formulas that are known formulas. I will supply these formulas to you on the exam. You have the sum as I goes from 1 to n of I squared is going to be n times n plus 1 times 2n plus 1 over 6. And the sum as I goes from 1 to n of 1 is just n. So we're substituting those formulas into our expression here, and we can eliminate the sigmas in our expression. So we end up with the limit as n goes to infinity, and we substitute it in there, and we get n times n plus 1 times 2n plus 1 over 6n cubed for that first term, and then the second term is simply 2 over n times n. And that's just going to give us 2. All right, and so then we go ahead and evaluate. You know, you can cancel out an n there, but the degree in that first fraction, the degree of the numerator and the denominator are the same. And so all you're really doing is looking at the coefficients, the leading coefficients of the numerator and the denominator, to evaluate the limit as n goes to infinity. Remember, this is just a limit at infinity. And so if the degrees are the same, you can just look at the dominant terms and look at the coefficients of the dominant terms. So this ends up giving us 2 over 6 plus 2, which is just 1/3 plus 2, or 7/3. And so that is the value of this particular definite integral. Now don't forget that that has an area interpretation in our problem, that the integral from 0 to 1 of x squared plus 2 describes this region. You're talking about the function x squared plus 1. Let's say that that's 0, 1 right there. This is a parabola, and that's 1, 0 right there. The function's up at 3, like so. And so you're getting this parabola with a vertex down here, and you're getting, and that's kind of a little bit of an exaggeration for the curve, but you get the idea because it's a parabola. And so we're talking about the area of this region right in here. Right, this is what we're finding the area of. And so we've got that the area of this region is equal to 7/3. So one interpretation for an integral is that the integral from a to b of f of x dx, if the function f sits above the x-axis, that this integral gives us the area bounded by x equals a and x equals b. And so we're talking about the area of this region right in here, right, for this function. And so this would be equal to the area here. That's our region right there. Now, if you think about this for a second, if we continue to look at this, and we're going to explore this a little bit further in a minute, but if our function is below the x-axis, if this is the graph of the function f, that's x equals a and that's x equals b. You know, if you think about a rectangle that's sitting inside here, that, you know, we were using the heights of those rectangles when we were calculating our limit of our sum. But these would be negative values in this case. And so in this particular problem, when you have a curve that sits below the x-axis, if you're looking at an area here, well, our definite integral does not give us the area of that region because you get the wrong sign on the heights of these rectangles because those function values would all be negative. And so if you're talking about the area of this region right here, in this case, the integral from a to b of f of x dx gives you the wrong sign. So it gives you the opposite of the area of that region. Or what you might say, and this is frequently the case, is that the area is the opposite of this integral. Now this is definitely an important idea that we kind of want to explore, is this connection between definite integrals and areas. Now, remember, one thing we did last time is sometimes, you know, if you have this connection between area and definite integrals, that on occasion you can encounter a function where the region that's generated is actually a nice regular geometric figure. So like, for example, in this particular definite integral, the integral from 0 to 2 of the function 3x plus 4, well, 3x plus 4 is a line, and when you graph that and look at the region bounded from x equals 0 to x equals 2, so at x equals 0, the function is at 4. So let's say that that's 4 right there. We're counting by 2's. So that's at 4, and then 6, 8, 10. Here's 10 right here. And at x equals 2, let's say that that's x equals 2, this function would be up here at 10. And so, you know, the graph's a line, right? The line continues on in both directions like this. But for the purposes of this problem, we are looking at the area of this region like so. But what's the deal here is this is a trapezoid. So the region is a trapezoid. And so if we were going to evaluate the definite integral, we could just find the area of this trapezoid, where this distance, that's one of the bases of this trapezoid, is 10, right? That's that length right there. This length over here is 4, and this length right here is 2. And so this definite integral, in this case, would simply be the area of this trapezoid, where the area of the trapezoid, remember we talked about this formula last time, was 1/2 times the height of the trapezoid times the sum of the bases. And so the height of the trapezoid, this is a trapezoid that's lying on its sides, this would be 1/2 times 2 times 4 plus 10, like so. And so you end up with 14 as the value of this definite integral. And we got that because the region that was describing this definite integral, it would happen to be a regular region. And so we could find its area just from this unknown geometric formula. All right, so now let's explore a little bit more in detail some things about area and integrals. So sometimes, it doesn't happen very often, but sometimes a definite integral could actually be evaluated with a known geometric formula. All right, so let's look at some examples. Let's look at some pictures here. And when I say examples, in this case, we're looking at different kinds of regions and how they're connected, how different areas are connected to definite integrals. So here we have a graph of a function f, and so I'm looking at the region that's bounded between -2 and 3, let's say. So we're talking about this region in here, and because this region is entirely above the x-axis between -2 and 3, then what we can say is that the area for this region is simply the definite integral from -2 to 3 of f of x dx. Now, what I think is a good idea to do is to draw in kind of a representative rectangle in the region here. This is going to become more important to you as you move through calculus, that you, when you're talking about regions here, you kind of identify an approximating rectangle and think about what that approximating rectangle looks like. For one thing, the width of it's going to tell you the variable of integration. So in this case, this width is delta x, and so that tells us we're integrating with respect to x. The height of this rectangle is the function value that we're talking about, right? That's our f of x right there. So think about this in terms of how it's connected to area. All right, so now what happens if the region that we're talking about is below, or partly at least below, the x-axis? So let's say we have a curve that is a parabola, and let's say it crosses at x equals 2, and then again at 8 right here, and it has intercepts at 2 and 8, like so. And let's say we have this parabola. We don't really care too much about what the equation is at this point, so we'll just identify this as some function f, and we are looking at trying to identify the area where, the area of this region between x equals 2 and x equals 6, like this. So this is the region we're after, and we want to write a definite integral that gives us this area of this region like this. Now, what's the problem here? If you look at a approximating rectangle, the approximating rectangle is down below the x-axis, and that function value is negative there. And so this integral would give us the wrong sign on our area. So if we're going to look at the area of this shaded region right here, we would write the integral from 2 to 6 of our function f of x dx. The problem is that integral, because the region is below the x-axis, gives us the wrong sign. And so to look at the area, we would stick a negative sign in front of the function. We'd change the sign of that in front of the integral. We'd change the sign of that integral. And that would give us the correct sign for area in this problem. Okay, so let's move on. So let's talk about a curve that looks like this one. So we're looking at different situations for every problem here. Let's say it has intercepts at 3 and at 0 and at 5. Like that. So at -3, at 0, and at 5 it has intercepts. And this graph kind of looks like this. It comes down below the x-axis, and then it shifts above the x-axis, and then comes down like this. And we are after the area of the shaded, and this is our function of f of x. That's our graph. And we are after the area of the shaded region, and this is the shaded region. In this case, it comes in 2 pieces. And notice the problem here is that part of that region is above the x-axis and part of it's below the x-axis. So if we refer to this, our area as the, let's say that region is A1 and this region is A2 right here, then our total area would be simply A1 plus A2. Now A2 is easy. A2 would simply be our integral from 0 to 5 of our function. That region is above the x-axis. If we look at an approximating rectangle on that region, that approximating rectangle sits above the x-axis. Its function value is positive. But the other region, A1, this approximating rectangle sits below the x-axis, and so the area for A1 would be the integral from -3 to 0 of f of x. Well, that problem is that integral gives us the wrong sign for that area, and so that would have to be, we'd have to put a negative sign in front of that. And so that would change the sign of that integral and give us the correct SIGN, the correct sign here. So our area in this case would be the opposite of the integral from -3 to 0 of f of x dx plus the integral from 0 to 5 of f of x dx. Now what you could do is there is a way to write this as just one integral. And the way to write this as one integral would be to write this as the integral from -3 to 5 of the absolute value of f of x. Now, if you wrote it with an absolute value like that, then what happens if in the region where it's positive, you just get the function itself, and the region where it's negative, it changes the sign of the function. And notice you get what we've written right up here, just above it, the sum of these two integrals. So you can certainly write it that way, and you're definitely going to see it written that way. I want to make sure you understand that absolute value part right there. But from a practical standpoint, to evaluate this integral, what we're going to have to do is split it up into 2 integrals and change the sign of the first one. You really can't evaluate it necessarily with that absolute value in there. All right, so let's look at a problem that has some regular regions in it and kind of explore that idea a little bit more. So let's say we have a graph that looks like this. The graph is composed of several triangles. Let's say we get right, we have a graph that looks like this one right here. This is our function g, we'll call it. And we are after the area, let's see, so this is x equals 1 right here. Here's x equals 4, 5, 6, 7, 8, 9. Here's x equals 9 right here. And we are after the area, or how the area of this region and this region are connected to each other, and how they're connected to the definite integral right here. So now what you could do here, if you wanted to find the area of that shaded region, what you could do is you could simply write this as the integral from 1 to 9 of the absolute value of g of x, like so. But from a practical standpoint, what we would need to do is we would split this up as the integral from 1 to 4 of g of x dx. And then what happens from 4 to 9, this function's negative, and so you actually have to change the sign of the function here, or say change the sign of the integral, just like we've been talking about before. So this would be the negative of the integral from 4 to 9 of g of x dx, right? Like this. And so notice that negative sign in front of that second one actually will change its sign appropriately so that we can get the correct area. All right, and then what are the areas of each of these regions? Well, the area on the first one, these are both triangles. So the area of that first one is 1/2 base times the height. Remember, it's the triangle. So that'd be 1/2 times 3 times 3, or 9/2. That'd be the area of the first one. And that would be the value for that integral, would be 9/2. But the second region, this is below the x-axis, so when we look at the area there, which is 1/2 base, which would be 5, times the height, which is 3, we get 15/2. So that's the area of that second region. But when you evaluate the integral, what would you get? You'd get, sure enough, you'd get the opposite of 15/2. You get negative 15/2. That would be the value of that integral right there. Right, and so what happens, that's why we put that negative sign in there, so you would actually add these two areas together, and so the total area would be 24/2, or 12. All right, so don't forget that if you've got a region like this, and let's say the area of this region, and this goes from A to B right here, little a to little b. Let's say the area of this region that I'm shading right here is 4. And this is the function f right here, that the value of the integral from a to b of f of x dx would be equal to 4. On the other hand, if we have a region like this, and here's a and here's b, this is our function g, let's say. And let's say that the area of this region is 6 right here. Then what would be the value of the integral from a to b of g of x dx? It wouldn't be 6, it would be negative 6, because that region was below the x-axis. Okay, so kind of wanted to point that out a little bit, see how that's working out. And kind of show you the connection there. A couple of more pictures to draw. A couple of different situations we'd like to talk about here. The next situation, let's say we have a function like this. And let's say that this function is f. And then we have another function like this one. This function's g. Let's say that this intercept right here is at a, x equals a. The two curves intersect at B, and then this x-intercept for G here is at C. And if we're after the area of this region like this, well, what do we have to do here? We have to split this region up into two integrals. We need to find the area of this region and then add to it the area of this region right in here. And this is where these approximating rectangles kind of come in handy, because when you look at these approximating rectangles in this region, notice that this rectangle in this region is bounded by f on the top, but this rectangle is bounded by g on the top. And so that makes a difference, right? Those are two, that's why you have to split this area up here. So what do you have here? That the total area, A, would be A1, which is the area of this purple region, plus A2, which would be the area of this pink region right here. So you'd have A1 plus A2. And how would you write those as integrals? The first one would be the integral from A to B of f of x, because that would be the curve that bounds the rectangle there, the approximating rectangle, plus the integral from B to C, and then the curve that bounds the approximating rectangle is now G. And so you'd have to write it out as two integrals like that one right there. All right, so that's kind of a problem that involves several curves. So let's explore that a little bit. Let's look at another situation that might occur. Let's say we have two functions like this. Let's say here's our function f, and then here's our function g. Like that. Here's x equals a, and here's x equals b. And we're after the area between a and b bounded by the two curves. No longer bounded by the x-axis, but bounded by the two curves. So if we're after that area, what I want you to kind of observe here is that if you look at the area underneath f, so the area underneath f and the x-axis, it would be this region right in here, from f all the way down to the x-axis like this. Right, that shaded region would give us the area, or that would give us the integral for f. And then the integral for g between a and b would give us the area for the red region right in here. And so notice what happens when you subtract those two regions, you end up with the area that we were after, actually, the area right in here. So this ends up being a subtraction problem. Right, when we subtract the red shaded region from the black shaded region, we end up with this pink shaded region right in here, which is what we're after. The approximating rectangle in that region kind of looks like this. Notice that approximating rectangle is bounded by the two curves. And what would be the height of that rectangle? Well, the height of that rectangle would simply be f of x minus g of x. Notice you're getting subtraction there also. So those two things kind of connect to each other right here. So what we have is that our area, the area of the shaded region, should be the area underneath f between a and b. That would be given by this integral, minus the area under g, which would be given by this integral. And since the limits of integration are the same, and we're going to explore this property more in a little bit, but we can actually rewrite this as simple as one integral, since the limits of integration are the same. And we have the integral of f minus g dx. And notice that f minus g is just the height of that approximating rectangle. And so it makes sense that that region would just be the upper curve minus the lower curve. That's the way I like to kind of say this in a situation like this, is that it's upper minus lower. And what I want you to also see is that it doesn't end up, believe it or not, seems kind of counterintuitive, but it really doesn't matter where the two curves are. Now notice in this picture, both of the curves were above the x-axis, but what if they were, let's say they were both below the x-axis? If both curves were below the x-axis between a and b, so let's say that this is our function f, and this is our function g, like this. Here's x equals a, and here's x equals b. Notice these curves are both below the x-axis. And so if we're thinking about area and integrals, well, the integrals give us the areas, but wrong signs, don't they? And by the way, we're after this area that I'm shading right now, this area that I'm shading in black. If that's the area we're after, what would happen if I looked at the integral of g between a and b? Well, g is below the x-axis, right? And so the approximating rectangle for g looks like this. right? And it's going to give you the wrong sign. But what happens when you look at the integral for g? If you look at that red up there, that red approximating rectangle, you know you're going to get a negative value. So, and what does it do? It gives you the area of this region that I'm putting in red right here. It gives you the opposite of this area. Right? And so, like, let's say, for example, that that this was equal to the red region up there, its area was 6. So then this integral would give us -6 right here. And then what about the integral for f? Well, the integral for f, you know, if you integrate f, now you're looking at this region, and I'm shading this in blue right here. It still gives you the wrong sign, doesn't it? And so the integral from a to b of f of x dx, now that blue region is certainly smaller than the red region. So let's just say, for argument's sake, that this area was -2, like so. Then what would be the area of the region we were really after? Remember, that's this shaded region right in here. And notice if I take, you know, if the area of the red shaded region is -6, and the area of the red shaded region, red striped region is -2, then the difference in those is 4. So our pink shaded region should have an area of 4. And notice when you look at upper curve minus lower curve right here, and you think about it along those lines, then notice this is going to be -2 minus -6, and sure enough, that does give you 4. It gives you the right sign. So the moral to the story here is that I want to point out is that it doesn't matter where the curves are. If you have an upper curve and a lower curve situation, and you're looking at the area bounded between two curves, area bounded between two curves, it's always going to be equal to this idea of upper curve minus lower curve. Doesn't matter where the two curves are, whether they're above the x-axis or below the x-axis. It's always going to be upper curve minus lower curve. So that's kind of a nice thing, that it doesn't matter how they're oriented as far as upper and lower like that. All right, so let's keep on moving. Our next stop. So that's a little bit of a discussion about area and definite integrals. And so our next stop is to look at evaluating integrals, evaluating definite integrals. And so to evaluate definite integrals, the first thing I want to kind of talk about is these are called the fundamental theorems of calculus, and you've got fundamental theorem of calculus part 1 and the fundamental theorem of calculus part 2. Interestingly, it depends on the book you're using, a textbook you're using, as to which one is called part 1 and which one is called part 2. It actually changes from problem to problem, or from book to book, as far as which one they're going to refer to as part 1 and which one they're going to refer to as part 2. The textbook that we're using, this OpenStax textbook, goes like this. And this is our fundamental theorem part 1. So fundamental theorem of calculus part 1. And the fundamental theorem of calculus part 1 goes like this, that the derivative, it states that the derivative with respect to x of this function, and this is kind of a crazy function, it's a function that's written as a definite integral from a to x of f of t dt, like so. And it simply states that the value for this derivative, right, this is the derivative of an integral, is simply the function f evaluated at x, like this. All right, so what this is actually doing, you've got a derivative with respect to x, and you have a function of x, but the x occurs as the upper limit of integration. If you looked upon that as an area, you've got this function f like this, and you're going from a out to x. And so sometimes I'll refer to that integral as what I call the area so far function. And because it's the area, here's our function f of t right here. This is the t-axis right here. And what are we doing? We're calculating the area from a out to x, but x is changing, right? X is our variable. That's what this integral is a function of. It's a function of x, right? And so that upper limit, that right boundary on that region kind of can move around. It slides around. A is a constant, but x changes. And so, you could be talking about x right there. You could have the exact same function, which I'm probably not going to draw a very good job of the exact same function, but let's say it is, and that's a, and maybe x is out to here, right? And so notice now it's changed, and the lower limit stays the same, the upper limit is moving from left to right. And so that's a variable, right? So this is a variable, and so it can move around. So that's why I call it the area so far. It's the area so far from a out to x. And what's this theorem really stating? This theorem's really kind of stating that if you differentiate or you look at the rate of change of an integral, that it's just the function itself. And so really what it's kind of saying in some ways is that the derivative and the integral are kind of like inverse processes in many ways. And so that when you apply both of them, it's kind of sort of like you're not doing anything at all. That's not entirely what's happening there, but that kind of gives you some idea of one thing that it's implying is that the derivative and the integral are kind of inverse processes of each other. So if we have capital F of x, if this is our function, and it's the integral from 1 to x of t squared over t squared plus 1 dt, and this is 1 out to x right here. So this is if we're looking at f prime, right, f prime would be the derivative of this function with respect to x. And this would simply say that this, applying fundamental theorem part 1, would simply say that this is just x squared over x squared plus 1. Like that. It'd be that simple to evaluate the derivative of that integral, which is actually a function of x. So that's easy enough. If you had capital F of x is the integral from 1 to x of the 4th root of t dt. And you wanted to look at capital F prime. Once again, that would be the derivative of this function from 1 to x of the 4th root of t dt, and that would be the 4th root of x, like that, right? Applying the fundamental theorem part 1. Now, one thing you do have to be careful about is, these first two problems are both functions of x, but if you have your function defined like this, the function from 2 to x squared, by the way, that lower limit, it doesn't matter whether it starts at 0 or at 1 or at 2. It's just at any constant you can evaluate using this fundamental theorem part 1. So let's say we have this function. So notice this is, what's f? F is a function of x squared. And so this is a chain rule problem if you're going to calculate the derivative. Because this is a function of a function. It's this integral function of the x squared function. So capital F prime of x would be the derivative of, or integral, this function of x, like this. And so applying the fundamental theorem part 1, this would just be 1 over our function t cubed, but evaluated at x squared, evaluated at the upper limit, like that. And then, but then this would be multiplied by the derivative of that upper limit, which would be 2x. And so this ends up being 1 over x to the 6th times 2x, or 2 over x to the 5th, like so. And that would be the derivative of that function right there. So this would be a chain rule problem, and this is where the chain rule comes into play, is that step right there, where actually this step right here, where you've got the derivative of the outside function, which is our integral function, and then the derivative of the inside function, which was the x squared function. All right, now that's the fundamental theorem part 1, but from, that does establish a nice connection between the derivative and the integral, and it gives you some idea of what a rate of change for an area would be represented by. That's just represented by the function itself. But from a practical standpoint, for evaluating definite integrals, that doesn't do you necessarily a lot of good. So we've got the fundamental theorem part 2. The fundamental theorem part 2, which is in particular of use for us if we're going to try to evaluate a definite integral, just in general. And this fundamental theorem part 2 goes like this, that the integral from a to b of f of x dx is simply equal to the capital F of b minus capital F of a. And notice that's capital F there, not little f. And so remember what capital F is. We kind of used this notation before, where capital F is any, emphasis on the word any antiderivative for little f. And this is kind of a direct consequence of our fundamental theorem part 1. So when I say, remember that capital F is any antiderivative, remember that that means, i.e., that capital F prime is equal to little f. You're looking for, the antiderivative is simply a function whose derivative is little f. So what the fundamental theorem says is that if you're evaluating a definite integral, if you can write down an antiderivative for the function, then all you have to do is find the antiderivative and evaluate it at the upper limit of integration and evaluate it at the lower limit of integration, and then subtract them, and you can evaluate the definite integral. So this ends up being a really nice, slick little theorem, and this is a huge consequence for us as calculus students for a lot of different reasons. One, maybe the most direct reason, it allows you to evaluate definite integrals much more efficiently. So like here's an integral from 0 to 4 of 2x plus 1 dx. This is a problem we did earlier. The region is just a trapezoid, but we don't have to, in fact, we found that this area was 20, and we found this before. We found 20 earlier as an area of a trapezoid. I think I did that problem on the last lecture. So the definite integral gives us another way to evaluate this, and it says simply write down an antiderivative for 2x plus 1. Now we've talked about antiderivatives now, so we have all these rules for evaluating antiderivatives or finding them, the power rule and the sum difference rule and the constant factor rule and all that, the log rule. So the antiderivative for 2x would be x squared. The antiderivative for 1 would be x, and we're going to evaluate that antiderivative from 0 to 4. And this is a notation I will use for evaluating it at the limits of integration, is I'll just put a vertical bar after the antiderivative and put the 2 limits of integration there. And then what do? We evaluate this antiderivative at the upper limit. We evaluate this antiderivative at the lower limit, and then we just subtract them. By the way, when I wrote the antiderivative down, notice I did not put a plus c down, that arbitrary constant that we talked about so much when we were looking at antiderivatives. And remember that this theorem talks about any antiderivative that you can write down. And so we just assume that our constant, our arbitrary constant, is 0 here, which makes the most sense since it says we can use any antiderivative to do this. All right, and so then what do we get? We get 16 plus 4 minus 0, and sure enough, we get 20. And there's our value of our antiderivative, or our definite integral there. All right, so that works out nice. We talked about a problem like this a while back. In fact, we talked about this exact problem. We talked about how this would be a difficult definite integral to evaluate if you're looking at the limit of a sum here, that would be a hard problem to go through. But using the fundamental theorem part 2, this is not a bad problem at all, because we just find the antiderivative or an antiderivative for x cubed using the power rule. That would be 1/4 x to the 4th. And we evaluate that from 3 to 7, like that. So remember, 1/4 x to the 4th using the power rule is an antiderivative for x cubed. Remember, we just let the arbitrary constant be 0. And so we've got that. So now we just have to evaluate that, antiderivative. So we evaluate it at the upper limit. We evaluate it at the lower limit. And I don't know why I put the powers like that. These powers should both be 4th powers. I'm not really sure what I was doing there. So that's 4th powers like that. That looks better. And so that gives us 2,401 over 4 minus 81 over 4. And so that gives us 2,320 over 4, which actually reduces to 580. And so that would be the value of that definite integral. It's important that you think about whether these definite integrals can be interpreted as area, because remember, a definite integral does not have to be interpreted. It doesn't have to be the case where you could interpret it as area, but this is a problem where we can evaluate this as area. This is the function x cubed. Now this is a gross distortion of what x cubed looks like, but you know, x cubed has a graph that kind of looks like this, right? And what are we doing? We're looking at the area bounded from 3 to 7. Remember, this is a really rapidly rising function. And so what did we just find in our definite integral from the previous page? From the previous page, we just found that the area of this integral is the integral, or the area of this region, rather, is the integral from 3 to 7 of x cubed dx. And we just found that to be 580, right? And you can interpret it as area because that region is entirely above the x-axis from 3 to 7. All right, let's continue on. So let's look at another example. Let's say we have the integral from 1 to 3 of 3x squared plus 4x dx. So using the fundamental theorem, we write down an antiderivative for 3x squared plus 4x. And that antiderivative, or remember, you can write down any antiderivative you want. So using the power rule, this would be x cubed plus 2x squared. And then this would be evaluated from 1 to 3. So at the upper limit, this would be 3 cubed plus 2 times 3 squared. There's our upper limit, minus the lower limit, which would be 1 cubed plus 2 times 1 squared, like that. Right? We evaluate at the upper limit, we evaluate at the lower limit. This is capital F of B. This is capital F evaluated at A. And remember, this is capital F of X right here. That's our antiderivative. So what do we get here? We get 27 plus 18 in the upper limit, and then the lower limit we get 1 plus 2. So you get 45 minus 3, you get 42 is the value for this region. If you think about the graph of 3x squared plus 4x, between 1 and 3, this is always above the x-axis. And so this could be interpreted, this is definitely a problem where 42 could be interpreted as area. Right, this is, if you look at the graph of 3x squared plus 4x, it's a parabola that has a vertex. I think the vertex is actually sitting below the x axis. Well, let's see. We could look at the graph of that. So you're looking at the graph of 3x squared plus 4x. Yeah, no, I was wrong. The vertex, take out the x. You have 3x plus 4. So the x-intercepts for this parabola are x equals 0 and x equals negative 4/3. So yeah, right. So I was right. And so, you get, and again, this is not exactly the way this graph looks, but 42 is interpreted as, could be interpreted as area here. This is a graph that goes through 0, 0, and it goes through negative 4/3, 0. So you have this parabola like this, and it's opening up, like so. But what are we doing here? We're looking at the area underneath this parabola between 1 and 3. Right, that's what we just found. So this parabola is a pretty steep rising graph. And so we're finding the area of this region. We found it to be 42, which is a fairly large area, and it makes sense that that would be true in this problem. All right, so now before we do anything more with evaluating definite integrals, let's go ahead and look at some basic properties for definite integrals. And these are all kind of properties that you could kind of think about in terms of area. So basic properties of definite integrals. All right, so the first property is that the integral from a to a of f of x dx. So if the limits of integration are the same, now remember that when you are looking at an integral, the integral from a to b, like this, if the curves above the x-axis can be interpreted as area, like that, right? So that's the area from a to b of f of x dx. So, if you thought about it that way, if you're looking at the area from a to a, right, now you've just got that line segment right there that you're looking at the area of. And so what should be the case here? That this area ought to be equal to 0. Because it's the area of a line segment, which really has no area. Or another way to look at this, certainly, is that, remember, the delta x is b minus a over n. But if b and a are the same thing, then you got a minus a over n, you're going to get 0. Right? So if the limits of integration are the same, you're going to get 0 as the value of the integral. All right, property 2. If you've got the area, the integral from a to b of f of x dx, that would be the opposite of the integral from b to a of f of x dx. So in other words, if you switch the direction of the limits of integration, then you're actually changing the sign of the integral. You could definitely see that by thinking about our delta x formula. You have b minus a over n for delta x, but if the limits of integration are backwards, you've got a minus b over n, and that's going to have opposite sign. And so you're actually changing the sign of the integral when you flip the limits of integration like that. The third property, kind of surprising in some ways, geometrically, at first at least, but is that the integral from a to b of f of x plus the integral from b to c of f of x is equal to the integral from a to c of f of x. Like so. Now this problem, or this property, I should say, seems to make sense, definitely, if you think about this picture, that if you're looking at the function f, right, here's a, here's b, here's c. Yeah, well, it makes sense that last integral is the integral from a to c. The first integral is from A to B, so it gives you the area of this region in here that I just shaded. The second integral from B to C gives you the area of this region, like this, and it makes sense if you add those two together, you ought to get the area of the big region. Though I do want to point out that I drew this specifically so that B was between A and C, but the property doesn't say anything about where B is. Property does not say that B must be between A and C. Okay, so what if B was not between A and C? So if B was not between A and C, so let's say here's your function f, here's A, and here's C, but B, notice, is out over here. So B is not between them. This property, what we're saying is this property still says that if you look at the integral from A to B of our function f, plus the integral from B to C of our function f, that you should get the integral from A to C of our function f like this. So, okay, so how does that make sense in terms of this picture? Well, the first integral from A to B gives us this area right here, the area of this big region. The second integral from B to C, notice the limits are backwards. And so what does that second integral give you? The second integral gives you the opposite of the area of that region right in there. The curve's above the x-axis, so it would give you the negative of that area. And so notice what happens when you take the big area A and you look at the negative of that little area. It's like you're subtracting. And so what ends up happening, you end up with the integral from A to C when you subtract. So it does make sense that that doesn't matter where the B value is. It doesn't have to be between. All right, the next properties, we've actually already kind of been using these, but the next properties talks about the integral from A to B of k times f of x dx. And this property it tells you that just like with indefinite integrals, that if you have a constant factor, that you can always take that constant factor outside of the definite integral if you wanted to evaluate that. Makes sense because you can do that with antiderivatives. And then the same thing for addition and subtraction, that if you have the definite integral of f of x plus or minus g of x, like that's equal to the definite integral from A to B of f of x dx plus or minus the definite integral from A to B of g of x dx. And again, you can do that for antiderivatives, so it certainly makes sense that you ought to be able to do that. All right, so the next couple of problems kind of relate to these properties a little bit and using these properties. So, and I would want you to be able to use properties to write out some values for integrals like this. So let's say that we have, we're given, now we know how to calculate this now, but let's say we're given that the integral from 2 to 4 of x cubed is 60. And by the way, it is. We could calculate that to verify that that's true. And the integral from 2 to 4 of x dx is 6. And the integral from 2 to 4 of dx is equal to 2. So let's say we're given those things. And again, using the fundamental theorem, we could now evaluate those and figure those out and see that those have got to be true. All right, and so then what about the values for these integrals then, based on those that first group? So what about the integral from 2 to 2 of x cubed dx? Well, we don't even need to use any of those integrals, do we? The integral from 2 to 2 of x cubed dx would be 0, right? Because if the limits of integration are the same, you always get 0 as the answer. All right, what about the integral from 4 to 2 of x dx? Well, the integral from 4 to 2 of x dx should be the opposite of the integral from 2 to 4 of x dx, right? And so what do you get, right? Because remember, when you flip the limits of integration, you should be changing the sign of the integral. So this should be equal to -6 right here, based on that middle integral at the top. All right, if we had the integral from 2 to 4 of 8x dx, then we have a property that says that the 8 could be brought outside of the integral, right, as a factor. And then what do we have? Looking at the top, we have the integral from 2 to 4 is equal to 6 for x. And so this would be 8 times 6, or 48. That would be the value for that integral. All right, the next one, just looking at various different combinations for these properties. Let's say we have this integral, the integral of x minus 9 from 2 to 4. So what would we do? We would split this up as the integral from 2 to 4 of x dx minus the integral from 2 to 4 of 9 dx. 9 dx. That's better. And what do I know I can do there? I know I can take out that constant factor. So that would be minus 9 times the integral from 2 to 4 of just dx. And so what do I get? The integral from 2 to 4 of x dx is 6, minus 9 times the integral from 2 to 4 of dx, which is 2. So you get 6 minus 18, or -12. All right, so kind of went through and see how these properties are actually being applied when we're evaluating a definite integral. Now this problem involved, or this group of problems involved some specific functions. So let's look at some where the functions are not, some specific functions. So let's look at the integral from 2 to 5. Let's say that we're given this of f is equal to 6. So this is something that's given. And so let me erase example there. So this is given right here. And we're also given that the integral from 5 to 10 of f of x is equal to 15. All right, so if you're given those two things, those two statements, then what do we have? Let's see, now, let's see, an example. We're going from 5 to 5 of f of x dx. We know that would be 0. Right? Anytime you're looking at an integral where the limits of integration are the same, you're going to get 0. The integral from 10 to 5 of f of x dx would be equal to -15, because the integral from 5 to 10 of f is 15. The integral from 10 to 5 is -15. And then the integral from 2 to 10 of f of x dx. Notice we would be kind of stitching those two integrals together at the top, and that would simply be 6 plus 15, or 21. Okay, so one more situation. Let's say we're given that the integral from 2 to 10 of f of x dx is 20, and the integral from 2 to 6 of f of x dx is 8, then what would the integral from 6 to 10 of f of x dx be? Right, so if you're looking at this, you can kind of piece some things together here on a number line, or on the coordinate system. See, you have the integral from 2 to 10, 3, 4, 5, 6, 7, 8, 9. Here's 10 right here. Here's 2. So that's what our first integral is, from 2 to 10. And then the second integral is from 2 to 6, like this. And what are we looking for? We're looking for the integral from 6 to 10. And what would have to be true? That those two integrals right there, when you add them, should be equal to the integral from 2 to 10. So the integral from 2 to 6 we've got was 8. and the integral from 2 to 10, which is this one, we've got to be 20. And so what should the value of this integral be? This should be 20 minus 8, or 12. Right? This would have to be 12 down here in order for this to work out, right? Okay, so another way of kind of looking at how this is all connected. All right, let's continue on. Let's look at a few more definite integrals, and then we can finish this with some applications. So our next example, so it's another example of using the fundamental theorem. So let's go from 1 to 2 of 3 over x squared minus 1. All right, so if we're going to write an antiderivative, if we want to use the fundamental theorem here, we need to write an antiderivative. And so the first thing we're going to need to do is go ahead and write this so we can use the power rule like this. So you bring the x squared to the numerator, and you get 3x to the negative 2. And now we're ready to write an antiderivative using the power rule. We add 1 to the exponent, put the reciprocal in front, which gives me negative 3. The antiderivative for 1 would be x, and this is going to go from 1 to 2. So this would be negative 3 over x minus x from 1 to 2, and then you would evaluate this. I would get rid of the negative exponent to evaluate this integral. So this would be negative 3 over 2 minus 2. There's our upper limit, minus the lower limit, which would be negative 3 over 1 minus 1, like that. So negative 3 over 2 minus 4 over 2 would be negative 7 over 2, and then minus negative 4. So that'd be negative 7 halves plus 4, which is 8 halves. And so you end up with 1/2 as the value for this particular integral. I do also want to point out that this could not be interpreted as area, and the reason why we know it can't be interpreted as area is look at where this function is between 1 and 2. At x equals 1, when you substitute that into our function, you get 3 minus 1, which is 2. So the function's up here at x equals 1. And let's kind of change the scale a little bit. Let's say that that's 1 right there. So there's where the function is. And then at 2, well, then you get 3/4 minus 1, which is negative 1/4, which would mean down here somewhere. And so what happens? The graph has got to cross the axis somewhere in between. And sometimes the function's above the x-axis, sometimes it's below the x-axis. So this 1/2 is not directly an area in that picture there. So I want you to kind of keep that in mind. All right, don't take a problem that looks like it might be difficult and make it, but it's actually easy. Don't make it a difficult problem. So let's say we have the integral from 0 to pi over 4 of 1 minus sine squared theta over cosine squared theta d theta. Now first, a lot of times when I see students do a problem like this, they really tend to freak out because they're not sure what to do. Here you've got all these trig functions here. But, remember what 1 minus sine squared is equal to. It's equal to cosine squared. And that's over cosine squared. And so notice those divide out. And so you get from 0 to pi over 4, you just get the integral of d theta. Or 1 d theta. And so this would simply be theta. That's our antiderivative from 0 to pi over 4. And boom, this ends up being an incredibly easy problem. You just end up with pi over 4. Technically, pi over 4 minus 0, but that would just be pi over 4. So don't overlook trig identities and some simple algebra in problems like this. All right, our next problem. let's look at one more definite integral before we finish with a few applications. So we're going, the integral in this case is the integral from -8 to -1. And this is x minus x squared over 2 times the cube root of x. All right, so now let's clean this up a little bit. First of all, that 2 in the denominator, don't get hung up with constant factors like that. Your only options here are to divide this out term by term. So that's what we're going to do. This is the integral from -8 to -1. This is x minus x squared over x to the 1/3 power dx, like this. So we're going to have to use algebra to divide this out. And we divide it out term by term. So this would be x over x to the 1/3 minus x squared over x to the 1/3. Like so. Then subtract exponents. And we're going to try to write this in a form so we can use the power rule. So when you subtract exponents, you have x to the 2/3. And then you have x to the 4/3 over x to the 1/3, which, I'm sorry, x to the 6/3 over x to the 1/3, which would be x to the 5/3. So this is x to the 5/3 right here. And now we are ready to use the fundamental theorem. We want to write down an antiderivative. We have the power rule for antidifferentiation we can use. And so what do we have here? Well, add 1 to the exponent, you get x to the 5/3. Put the reciprocal in front, which is 3/5. On the second term, you add 1 to the exponent, you get x to the 8/3. Put the reciprocal in front, which is 3/8. And this is going to go from -8 to -1, like that. So we've written down the antiderivative, and now we're ready to evaluate it. And this gets to be very messy from here. So a lot of times the arithmetic is pretty nasty. So you have, at the upper limit, right, I have -1 to the 5/3 right there, minus 3/8 times -1 to the 8/3. Put parentheses around that, minus, and then you're putting in -8, so you have 3/5 times -8 to the 5/3, minus 3/8 times -8 to the 8/3. Yuck. Right, so this is pretty nasty arithmetic here. So you have -1 to the 5/3 is just -1. So you end up with -3/5 right there. And -1 to the 8/3, because the 8's even, that ends up being +1. So you end up with minus 3/8. So there's my upper limit. And then the lower limit, you have -5 to the 5/3. -8 to the 5/3 is the cube root of -8 to the 5/3, which is -2. To the 5th is -32. Then times 3 gives you -96 over 5, like that. And then you have -8 to the 8/3 power, which is -2 to the 8th power, which is, believe it or not, 256. And so you get minus 768 over 8 on that term. Wow, like that. And now the least common denominator there ends up being 40. And to simplify things, I did this problem ahead of time. And I got, and so you need to check my arithmetic here, but I got 4,569 over 40 for the answer there. So you check my arithmetic and see if that's correct. I believe it is, but please, actually that's 4,569 over 80. I'm sorry, I miswrote it. 4,569 over 80. There you go. All right, so check my arithmetic on that. Check my arithmetic. All right. So now we are going to finish the day with 2 applications for integrals, and that will finish up our class day today. One is, so let's see, so applications. The average value of a function, between A and B is given by, and it's an integral, believe it or not, given by 1 over b minus a times the integral from a to b of f of x dx. And when I say the average value of a function, that's our function is f of x right there. So you just simply take the integral from a to b and you multiply it by 1 over b minus a, and you actually get the average value of the function between those two values. So, you know, the function takes on an infinite number of values if it's a continuous function between two numbers a and b. So it's like if you took all those infinite numbers, which you really can't do, but if that's what you know, that would be one way to think about it. And then you're finding the actual average value between those two x values. So as an example, if we have f of x equals cosine x, and we were looking at between x equals 0 and x equals pi over 2. Okay, so as a graph, not to scale at all, but if that's 1 right there, and this is pi over 2 right here, you know, this, we know that the cosine graph looks like this, right? It continues on, certainly, but that's one piece of the cosine graph. So what's the average value of the cosine between 0 and pi over 2? So the average value of the cosine would be equal to 1 over b minus a, so it'd be 1 over pi minus 2 minus 0 times the integral from 0 to pi over 2 of cosine x dx, like that. And so that would give us, let's see, so that'd be 1 over pi over 2 times, and I don't need to write out the integral anymore. I just use the fundamental theorem. So the antiderivative for cosine is sine. We're going from 0 to pi over 2. So this would be 2 over pi times sine of pi over 2 minus the sine of 0. Sine of pi over 2 is 1, sine of 0 is 0. You just end up with 2 over pi. And 2 over pi is approximately equal to, let's say 2 divided by pi is approximately equal to 0.6366. So that's the average value of the cosine between 0 and pi over 2. One way to look at that is that the cosine actually hangs around closer to 1 than it does 0 between 0 and pi over 2. So the graph's not symmetric there at all, and it's actually stays up closer to 1 for a longer period of time than it does getting down close to the x-axis. All right, so if the population of a city was given by P of t, like that, then the population, the average population, let's say let's say the time 0 equates to the year 2010, then the average value, then the average population between 2010 and 2016 would be given by this integral, would be 1 over 6 minus 0, would that be 1 over b minus a, times the integral from 0 to 6 of our population function, p of t dt. So that would actually be our average population there. All right, so that would just be 1/6 times the integral from 0 to 6 of p of t dt. So integrate the population function, divide it by 6, and you get the average population between 2010 and 2016. So that would be one application. All right, final application. We're going to talk about position and velocity. So remember that position is given by s of t, right? If you're talking about, let's say, an object that's moving on a horizontal line. So the object is moving on a horizontal line. And so s of t gives its position, and we know that s prime of t, the derivative of position, gives us velocity. All right, so what happens if we look at the integral from a to b of the velocity function? Okay, well, what do you have here? That the position is the antiderivative of velocity. If velocity is the derivative of position, then position is the antiderivative of velocity. And so using the fundamental theorem, this would be our position function, which is an antiderivative, evaluated at the upper limit, minus the position at the lower limit. So now what do those things represent? Well, this first one is the position at time equals b. And this one is the position at time equals a. And what are we doing there? We're subtracting them. And so what I want you to understand is that this gives you what we call the displacement in position. It does not necessarily give you total distance traveled. All it does is give you the displacement of the object. So if you're saying, for example, if you're saying that remember this object's moving in a horizontal line. If this is its position at time A, that would be s of A, and this is its position at time B, s of B, if you subtract them, you get the distance between those two, which is displacement, right? This is displacement, but it may not be distance moved. That's displacement right there. But what if the object did this? What if it moved to the left like this initially, and then it turned around at some time between A and B, and then came around this way and moved to the right? Then notice that the total distance that object's moved would be the red distance plus the blue distance, which would not be s of b minus s of a. So the integrating the velocity function gives you the change in the position of the object, but it doesn't give you necessarily the distance moved. If the object changes directions, then it does not give you the distance that it's moved. Okay, so let me give you an example of that we'll look at. So let's say I have v of t, velocity is equal to negative 2t plus 4. That's our velocity function. All right, and so we are going to look at the times between, we're going to look at the time between t equals 0 and t equals 6. All right, so now I want you to think about what the graph of this velocity function looks like between 0 and 6. All right, so here's our t-axis, and then this is our velocity axis right here. Right, and what are we given? That at time 0, just plugging numbers in here, right? At time 0, the velocity is 4, and at time 6, it is at negative 8. So that might be like right here. Right, that's at 6, negative 8 right there. And so what do we have here? That the object is actually, or if you graph the velocity function looks like that. So what have you got here? That the velocity is positive, right? The velocity is greater than 0 for between t equals 0 and t equals 2. And then what does that mean? That means that the object's moving to the right. And then v of t is less than 0 between t equals 2 and t equals 6. So that means the object's moving to the left. So notice that the object changes direction. The object changes direction at t equals 2. Right, t equals 2, the velocity is 0 there. Right, velocity at time 2 is 0. And the object's actually changing directions. All right, so what happens here? If we look at the integral of this function from 0 to 6, look at the integral of our velocity function from 0 to 6. Well, let's see, that would be we can actually evaluate this, right, because we have the function. This would go from 0 to 6 of negative 2t plus 4 dt. And so then this would be negative t squared plus 4t between 0 and 6, or from 0 to 6. The upper limit or the lower limit 0, so we don't have to worry about that. But the upper limit is going to be negative 36 plus 24, or negative 12. This is not distance moved. This is displacement. And we're saying that from t equals 0 to t equals 6, from t equals 0 to t equals 6, the object is moved, or changed positions, moved left 12 units. Now I want you to look at some other integrals here to see how this all kind of pieces together. If you looked at the integral from 0 to 2 for our function, so what do we get there? That the object is always moving to the right in that interval. So this will give you the actual distance moved, and it'll give you the distance moved to the right. Same antiderivative, negative t squared plus 4t. This would be from 0 to 2. And so at the upper limit, you get negative 4 plus 8. Lower limit is 0, you get 4. So that means that the object is moved 4 units to the right. So object from t equals 0 to t equals 2, object moves 4 units to the right. And then from t equals 2 to t equals 6, if we want to do that, we wouldn't have to do this because we have enough information to figure it out now, but we're going to do this. From 2 to 6, same function. Same antiderivative, all that's the same. It's just the limits of integration are different. Now the object's always moving to the left in that interval. So since it's always moving to the left, this should also give us distance because there's no change in direction here in this interval. So at the upper limit, you get negative 36 plus 24, minus at the lower limit, you get negative 4 plus 8. So that would give us negative 12 minus 4, or negative 16. So what do we get? That the object moves 16 units to the left in that interval. And then what happens? It makes sense that where does it end up? It ends up 12 units to the left. You know, you could look at how this works out at the bottom here. Right, that the object moved 4 units this way to the right, and then the object moved 16 units this way, right, minus 16. And so what should end up happening? If you look at the object's initial position here and its final position here, right, what happened? The object moved 12 units to the left. Right, and that makes sense. All right, so we wanted to look a little bit at what would happen if you integrated a velocity function, and you get displacement here. All right, so that's our lecture for the day. Covered a lot of kind of introductory material on the definite integral. And so now we are going to be ready to tackle on Wednesday evaluating definite integrals. We're going to spend the next couple of days talking about evaluating definite integrals. And that's kind of sort of where we're going to finish the semester out, is evaluating definite integrals and looking a little bit at applications. But most of the rest of the semester is going to be evaluating different kinds of integrals. Have a great day. Please remember that today is the last day to withdraw from a class. Hopefully, since you're listening to this lecture, this is not an issue for you. Please always contact me if you have a question. I'll be happy to talk to you about your grade. Remember, I have online office hours tonight and tomorrow night and Wednesday night. So don't hesitate to come by my online office if you have questions. Also, don't forget that your homework 5 is due next Tuesday, and that your exam 3 review will be posted by the end of the week this week. Have a great day.